Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy. Science rules.
Thank goodness it was a solid, not a liquid, or else it would have spilled everywhere.
But dear Sue, wouldn't it be even better if it were a gas so we didn't have to pick it up?
Whoa. Both of you guys are so smart. I wish I was as good at physics as you guys.
So let's talk about matter.
Well, basically, there are 3 different states of matter.
What are those?
Well, Jill, my shoes are a solid.
But that's only one of the 3 states of matter.
Correctamundo. The other 2 are gas and liquid.
So tell me about the states of matter.
Well, come with us.
Oh, I know what these are.
Oh, go on. Let me in on your vast cavity of knowledge.
If you insist, this is ice, this is water, and this is boiling water.
You're spot on with the ice and water, but what's going on above the boiling water?
Hotness.
It's actually water vapor, a gas.
Oh.
And as I'm sure you know, ice is a solid and water is a liquid.
But you should also know how they get to their respective phases. When a solid freezes, or when a liquid freezes, it becomes a solid.
Conversely, when a solid melts, it becomes a liquid.
Just think about it. You barely ever see liquid steel because it's a solid until it's been heated up to a very, very high temperature, which usually doesn't happen unless you're a blacksmith.
About a liquid to a gas.
Well, a liquid becomes a gas through evaporation.
But what is evaporation?
Evaporation is the change of phase from a liquid to a gas.
So basically, evaporation is when a liquid gets heated up and goes up, and away, and becomes a gas, which we can't see. So, yeah.
I like your shorts.
Oh, it's cold out there.
Oh dang. Yeah, it's cool. Cool place.
Gotta love phases of matter, right?
Yeah.
Science rules. Bill Nye the Science Guy.
Water has a relatively low boiling point, which means it becomes a gas faster than something like steel.
So you're saying a solid becomes a liquid when it's heated up, and then a liquid becomes a gas when it's heated up again.
Correctamundo.
Yay.
Now that we've got the general concepts, let's delve deeper into this rabbit hole.
Solids, unlike liquids and gases, have their own shape and don't conform to the shape of their container.
What?
He means if you put this Eiffel Tower in this glass, it will keep its shape. But if the Eiffel Tower was melted, it wouldn't keep its shape and it'd flow freely.
Most solids are made up of crystals,
Crystals are either regular or irregular shapes.
and many crystals aren't even visible to the naked eye.
Awesome. Can we make some?
Sure, we just have to let the salt water in this dish evaporate. Then we'll be left with salt crystals.
Ta-da! Here are the crystals. We did it! Now let's move on to something a little more practical.
And what might that be?
How about density? That sounds swell.
Density is how much matter is packed into volume. Density equals mass over volume.
So let's take a scale with 1 kilogram of feathers on one side and 1 kilogram of steel on the other. While they'll have the same mass, the volume of feathers will be much greater because you need more feathers to equal 1 kilogram.
So let's say that the feathers take up 2 meters cubed and the steel takes up 0.1 meters cubed. We can find the density of feathers by taking 1 kilogram over 2 meters cubed, which gives us a density of 0.5 centimeters cubed.
Oh, and we can do the same thing for steel, right?
Precisely.
That means we just need to take 1 kilogram divided by 0.1 meters cubed to find the density of steel, which would be
10 grams per centimeter cubed. Sorry, champ. I hate to interrupt. I was just one step ahead of you.
Just think about it. There's more weight in a smaller area of steel than there is in the same area of feathers.
I got it!
Now on to something more fun and stretchy.
You talking about elasticity?
Rightio! In simple terms, elasticity is expressed when an object is bent out of shape and then returns to its original form.
Take for instance this rubber band. When you stretch it back, you're bending it out of place. But because it possesses elasticity, it snaps back.
Okay, can you explain why the harder I pull the rubber band back, the more it stretches back?
Well, actually, Robert Hooke explained it first with Hooke's law. Hooke's law explains that the more force you put into an elastic object, the further it will bend. If we double the pull on this band, we double the force as well. And it snaps twice as much, too.
Well, that pretty much covers the basics of solids. Shall we move on?
Oh, heck yes! What's next?
I say we move on to liquids, the middle of the road.
As we learned earlier, solids don't adapt to their container, but liquids do.
Why?
Liquid has more thermal energy, so the molecules move more loosely, creating space between them and allowing them to flow.
As I'm sure you know, when a liquid fills up a container that's half a meter high and has a volume of 1 liter, it also obtains those properties.
The liquid is also pushing against the outside of the container on all sides, and pressure under the liquid increases as you add more on top.
Pressure is defined as force per area on which the force acts. Note, pressure doesn't involve volume.
The pressure under a 500-foot column of water is the same pressure as a lake that's 500 feet deep.
That's so cool. Why do we even go scuba diving then? Why don't we just go swimming in a column of water?
Well, that's a different subject, but speaking of swimming, do you know why we can swim in water but not air?
Liquids have properties of buoyancy, which means
Objects.
essentially lose weight in a liquid.
But how do they lose weight?
In any liquid, there's a buoyant force pushing up on any object in here.
This is why it's so easy to lift someone in water, but not so much on land.
Well, that's all fine and dandy, but let's talk about displacement when someone's actually put in the water.
What about displacement?
Do you know what it is?
No.
Let's fix that, dear Sue.
When you put an object in a container of water, the water level will rise by the volume of the object.
Meaning that a rock 1 liter in volume will basically push 1 liter of water aside, making the water level rise just that much.
But if you just put a piece of wood that is 1 liter in volume, then it won't displace 1 liter of water.
Because wood has a density less than that of water, so it just floats on top.
You're saying the reason metal doesn't float is because it's denser than water?
Yes, but not always. What about the Titanic? That was made of metal and it floated.
Maybe not the best example for things that float, but just think about any metal boat. It floats because its average density is less than that of water.
Let's say the iron frame itself is 8 times heavier than water. But just imagine that the air inside the ship is also part of the density.
Archimedes' principle states that any immersed object is pushed up by the buoyant force equal to the amount of liquid it displaces.
And because the density is less than that of the water displaces, it floats.
Oh, I got it. You have to imagine the ship is a shape with a bunch of air in it. It's just like how if I suck in a bunch of air, I will float, but if I let it out, I will sink.
Correctamundo!
Ever heard the term sea of air?
Yeah.
That's like our atmosphere. And you may not know, but air is a fluid, and you can feel it if you move your hand side to side.
As you know, the entire bottom of the ocean is subject to the entire ocean's pressure.
Likewise, we are at the bottom of our sea of air, and we can feel the weight of 14.7 pounds pushing down on us at all times.
And if you go up in elevation, that pressure decreases a little bit.
So I can jump higher on Mount Everest?
Yeah, technically, but not that much. We could actually measure the atmospheric pressure if we had a barometer.
What's a barometer?
A barometer is made up of a glass tube of at least 76 centimeters long, filled with mercury.
Due to the way mercury behaves, we can see that atmospheric pressure on the side of the tube because mercury rises and lowers as you change.
Gas doesn't have a set mass, density, or volume, so its pressure is actually much greater in something like a car tire.
If there's twice as many air molecules stuffed into a car tire, the pressure is twice as great.
Regarding buoyancy, all of the rules discussed earlier about liquids still apply.
Yep. Now, since I can't think of a clever segue, let's just go to the conclusion.
Man, I sure learned a lot about the states of matter.
I bet you did. We're the best teachers in the whole wide world.
I think we're good.
That's like our atmosphere. Nope, nope, don't cut it, don't cut it. I said don't cut it.
I didn't.
Okay, now you can cut it.